So in this video, we'll be going over a high-level view of differential equations, just various examples of them, and also we'll be solving some first-order differential equations. It's a basically high-level view. It's an important topic in science and math. Examples are predicting over time the temperature of a hot liquid as it cools to room temperature. That's a famous problem called Newton's law of cooling, or it's a law. Can you predict the age of an artifact by analyzing the amount of carbon in the material? Can you predict the future population, exponential growth, or exponential decay? These are all types of differential equations, or types of problems where you would need to use differential equations to find the solution. In general, a solution to a differential equation is not unique. There may be several functions satisfying the same equation. For example, y equals sine x plus c is a solution of y prime equals cosine x for any real constant c. Remember, when we are dealing with indefinite integrals, there's always that plus c. So there's different solutions that could satisfy it depending on an initial condition that they may provide you. And yeah, in college, you'll most likely, if you're planning on pursuing an engineering background of some sort, or science and math, you will need to use differential equations. So they may require you to take a differential equations class. Here in future videos, we'll be going over Euler's methods, numerical solutions of certain types of differential equation systems, second order differential equations, exact solutions, and graphical illustrations of what these may look like. So first order differential equations. I think what we will do is, I'm just giving you a high level view. I believe this is provided to you guys. So this section will formally define differential equations and how to classify them by order and linearity. Here they give you have the function y equals e to the x squared. If you want to differentiate that, you use the chain rule. It's 2x e to the x squared. But here, this is something that you have to get used to, right? The derivative dy dx equals 2x times e to the x squared. E to the x squared is the same thing as y. So you would sub y back in for e to the x squared. And you get your function as dy dx equals 2x y. And that's usually how these problems will be displayed, as a kind of, you'll have both variables involved in the equation. Differential equation is an equation containing derivatives of one or more dependent variables with respect to one or more independent variables. So basically you'll have a dependent variable. Generally it's going to be y, which is dependent on x, and x is the independent variable. These are the formats that you'll see it in. Usually it's going to be dy dx. There's also partial differential equations. I don't think that's important here, but just a small example is when you have a multivariable function that's relying on two variables, then you can take the derivative of each one of these with respect to the other variable. So here, if you take a partial with respect to x, that means that y is a constant and it's treated as such. So here the derivative of that would just be 2x y, because y is just a coefficient of x squared. So you would treat x squared like the power rule, it would be 2xy plus this would be a constant, so that'd be 0. Partial with respect to y, then x becomes the constant. So then here you would have just x squared, because the power rule, the exponent of this is 1. So it'd just be x squared plus 2. And that's the partial with respect to y. But in this, for these examples, you're only dealing with ordinary differential equations. We also have examples like here where maybe there's a sine x involved, or a second order differential equation. This is considered a second order because the highest derivative of it is a 2. See here, the order of a differential equation is the highest order derivative in the equation. So this is first order ODE. So these are some examples. So this is a first order ODE because the highest order is 1. This is first order as well. It's just squared. They're just being silly and trying to trick you. This is second order. This is the notation for second order ODE. And then differential equations are classified by their linearity. A differential equation is said to be linear if all terms with dependent variables are first order. So all terms with dependent variables. So here you see the dependent variables is y, and y is it's by itself. It's it doesn't have it's not multiplying by anything. It's it's by itself. So this is linear. Here it's non-linear because this is a coefficient of the y prime. So you're eventually going to have to do like some manipulation, and eventually your solution is probably not going to be non-linear, or probably going to be non-linear. Here this is second order as mentioned, and it's linear because there's no multiplication going on with the y. There's no coefficient in front of the y, the dependent variable. This is second order nonlinear because you're taking a cosine of y. Right? Cosine is nonlinear function. It's a cyclical function that just goes, and so it's nonlinear. And this is an example of third order linear function. This is a coefficient, but it's a I forget the term, but it's it stays the same. So it's 7. It's fixed. So an ordinary differential equation is an equation containing only ordinary derivatives of one or more dependent variables with respect to a single independent variable. The order of a differential equation is the highest order derivative, and an ordinary differential equation is said to be linear if the dependent variable y and all of its derivatives are first degree. Right? So dependent variables first degree, and the coefficients of all terms with the dependent variables and derivatives depend only on the independent variable x. So here, so back to the initial example, this would be classified as a first order linear ordinary differential equation, because the coefficient of all terms with the dependent variable and derivatives depend only on the independent variable x. What's going on here? Okay. So here, well, they want to classify the ordinary differential equation here, right? And the way you classify these, right, is you figure out the order, and then figure out whether it's linear or non-linear. So here you see its order is first order because it's doing one derivative, or dealing with your first derivative. It's non-linear because the y coefficient is being squared. So that's going to be non-linear. The highest and only derivative is the first derivative, therefore it's first order. The y squared term makes it non-linear. I'm not sure what's going on here. Classify the ordinary differential equation here. We'll do right here. This is going to be second order, I believe linear. Yeah, second order linear because there is no term with a nonlinear y or a coefficient depending on y. It is linear, right? So no term with a nonlinear y, that's this, and nonlinear means it's exponent or, you know, whatever function. It's a linear function. It's exponent or it's a power of 1. And the highest derivative is 2, therefore it is second order. Classify this one. This is going to be first order nonlinear, right? Because highest order is 1, and the sign makes it nonlinear. And then here, classify the ordinary differential equation. It's second order, and it's going to be nonlinear because y, the coefficient of the y is dependent on x. There. This makes it nonlinear here. Let's go back to the coefficient of all terms with the dependent variable, and the derivatives depend only on the independent variable x. So where is it? Yeah. So here the highest derivative is the second derivative. The y dy dx makes it nonlinear. Okay, so now we'll be delving into separable equations. First order differential equation is separable if it can be written in the form of y prime equals f of x times g of y. So if you can write a function as a product of x and y, then it is considered separable. So for separable equations, it's more useful to use the dy dx notation instead of like y prime, because then you'd be able to separate the variables to get both on one side, and then you integrate the variables and you evaluate the integrals, and then you don't forget about the constants. Most of the times you'll be asked to express y in terms of x, but sometimes it's not necessary or possible, and the implicit equation is also fine. So and differential equations are similar. A general solution is one that still has a constant resulting from the integration. So when you do your integral, you'll have that plus c. That's considered a general solution. A particular solution is obtained if they give you a set of initial conditions, as you have here. So a general solution is just the antiderivative of the differential equation, or the solution for the differential equation. And then a particular solution is when they give you an initial condition and you eventually plug it back in and get something particular. Make sure you review your techniques of integration. That'll probably come up. Use substitution, integration by parts. I'm sure a few other techniques that you would need to remember. So yeah, we can go over these. Let's see. Okay. So here, we have, sorry. Whoa. Okay. I don't know if I like this device. Dang it. Okay. So here we're going to do, we're going to separate the variables and write down the integrals that we would need to solve. We're not going to actually solve the integrals. We're just going to do the algebra behind it. So here you have y prime over x equals e to the x over y. You would cross multiply. You can get y times y prime equals x times e to the x, right? And so now this is the same as y times dy dx equals x e to the x. And then here you would have y dy equals x e to the x dx. And here you would write those integrals there. And that's all you need to do for these examples. Just to show the solution. And there you go. Yep. So for that one, that's the solution for that. For the first one. So here, I'm just going to rewrite y prime as dy dx equals cosine squared x times cosine squared y. And then literally you're trying to separate them and get everything on one side. So this would be dy over cosine squared y equals cosine squared x dx. And then you would integrate this. And remember, cosine squared is the same as integral of secant squared y equals integral of cosine squared x dx. And you know that integral of secant squared is tangent. Okay. X times y prime times ln of y equals ln of x. So here you have x times dy dx times ln of y equals ln of x. Well, since this is all a product, we can bring all the x's on one side. So this is going to be the same thing as ln of y dy equals ln of x dx divided by x. And then you would integrate both of those. Okay. And then I'm going to erase a little bit here so that I have some space. And here on the last one, we have square root of 1 minus y squared, or 1 minus x squared, times dy dx equals 1 plus y squared. So then you would have, literally you can cross multiply this and bring and divide by that, and then divide by this. And I'm doing a lot of steps at once, but I think you can get it. So it'd be dy over 1 plus y squared equals dx divided by square root of 1 minus x squared. And you integrate those. Okay. So pretty straightforward. You're literally just doing algebra for these, so shouldn't be too difficult for that. But definitely practice those because, you know, you need to get used to that process or that thought process of here, determine whether y prime equals x plus y is separable. If so, find the general solution. I think it's safe to say, remember, it's separable if you can write dy dx equal to f of y times g of x. So you have to have a unique, you know, product between the two variables. And here we don't have that, so you know it's not separable. Determine whether this one is separable. Here you have dy dx equal to xy squared, and then you have dy over y squared equals x dx, right? So it is separable. First of all, it was already separable because you had the two functions that are product of each other. Now they want you to find the general solution. So here we do our manipulation. We have y to the negative 2 dy equals x dx. And here we integrate. integral of y to the negative 2 is going to be negative y to the negative 1 equals x squared over 2 plus c, right? So then here you would have 1 negative 1 over y equals x squared over 2 plus c. You could say this is the same thing as x squared plus 2c all over 2, because you could write that as 2c over 2 and then get common denominators. So then this is the same thing as y equals negative 2 over x squared plus 2c. You could write it however. I don't think it matters. So I think this would be an acceptable solution. So I think they may go a little further, you know, if you want to leave it as a constant there. So here, yeah, basically, you know, you can redefine c as another constant. You know, 2c as a constant, because it's just 2 times another constant, so it's just a constant itself, so it doesn't really matter. But so yeah. Determine whether this is separable. Remember, like I said, it's separable if you can write it as a product. So you have, So you have x dy dx minus y equals 1 minus dy dx. So here we're gonna get everything on one side, well, at least our dy dx is, and then this is gonna be y plus 1 on that side. So then here, if I factor out a dy dx, I have x plus 1 equals y plus 1. So then this is going to be dy over y plus 1 equals dx over x plus 1, right? So it is separable, right? Because technically here you would, oh crap. Technically here you could write this as dy dx equals y plus 1 over x plus 1, and that's your function to show that it's separable. So then here, we'll come over here, we'll have integral of 1 over y plus 1 dy equals integral of 1 over x plus 1 dx. And then you have ln of y plus 1 equals ln of x plus 1 plus c, right? In order to solve for y, to raise e to both sides, so you have y plus 1 equals e to the ln of x plus 1 times e to the c, right? Remember, you know, when you're adding exponents, you end up multiplying them. If you don't remember that, I'd review your exponent rules. And if you don't remember, e to the ln of x equals x, because ln is the same, ln of x is the same thing as log base e of x. And if you don't remember logs, God, I would review those. Here, e to the c can be written as this constant. So this would be y equals c e to the ln of x plus 1 minus 1. Okay. You see here. Yep. Well, and I can go one step further, obviously, because e to the ln of x plus 1 is just x plus 1. So, And in fact, you could probably go even further, cx plus z minus 1, which is just cx plus c, but doesn't matter. This is the solution here. So, okay. Next, they want us to find the particular solution of this differential equation. So remember, our solution was y equals c times x plus 1 minus 1. You just double check that. Yep. Okay, so that was our solution. So the particular solution would just be literally plugging that in. So we get negative 2 equals c times 1 plus 1, which is 2 minus 1. So c would be negative 1/2. So negative 1/2 x minus 1/2 minus 1. So it's y equals negative 1/2 x minus 3/2. Yep. So just plugging in that particular solution back in the equation to solve for c.